So we continue with the SFG, alternative to the simplification of the diagram of the control systems. This method suitable for complex structures, which is have a highly interwoven systems, a lot of variables. Okay, so these systems allows users to represent the variables in terms of nodes. Okay, like this. Okay, they can have branches. Okay, in this SFG we represent as line with the gain. Okay, if that line is no block, so they consider as a unity or one. Okay, let's say we have this simple closed loop control system diagram. Okay, in which we can represent this control system diagram into SFGs. So how we're going to do is that we identify the input first. Okay, this input we represent as one node here. Okay, and the outputs. Okay, the outputs we always represent as a CS. Okay, this one, if you remember, this one is a pick-off point, okay, between the outputs and the feedback block. Okay, and this one is a summation junction. Okay, also we represent as a node. Okay, this pick-off point also we represent as a node here. Okay, so how about the block or the box of the systems? Okay, we represent as a system GS and HS. So that one we represent as a gain on the line. Okay, between these two nodes we have a line. Okay, between these two nodes we have a line. Okay, for this line we don't have a block or system in between, so we just put unity as its gain. Okay, but for between ES and CS nodes we have GS, so that's why we put GS here. So for the case of the between CS and the summation junction, here we have this closed loop. Okay, so this closed loop is in negative value because this feedback value deduct by the input from the RS. Okay, so we notify SH in the SFG as a negative HS. Okay, got it? All right. Complex block diagram like this, we have multiple loops, more than one loops. The same thing we need to identify. Okay, which is the first thing we need to know the input, where is the output. Okay, so the input will be one node and output is a one node. So as you can see here, the pick-off point actually share the same nodes. Okay, share the same nodes here. Okay, so that's why here we just put one node. Okay, to for the outputs and for these two feedbacks. Okay, so and then we make a line. Before that we need to find all the nodes that we can identify. Okay, this one is a I can say it's the third node that we can find. The third node is between ES and the FS. Okay, we have here one, and we have here two. Okay, We also have here two nodes that share in one nodes. Okay, so we just put here one node. We don't need to add anything. But here we have another input. So this system, we have two inputs, one here, number 2, and this is number 1. You have two inputs. Okay, so be careful with the questions. What transfer function that according what transfer function that the question want, or what transfer function that you want to develop? Is it between the CS and RS, or between the CS and DS? Okay, so that's the thing that you need to notify before you make a solution or make a reduction. Okay. So we go back to the SFT. So between the ES and FS, we don't have a block, we don't have a gain, so we put unity here, 1 and 1. And then we have these nodes again. I'm sorry, I missed this one. We have another one nodes here. Okay, so we connect all the nodes by one line at first. Okay, we make one line like this at first. Okay, this is a step that I can show you. Okay, although they already draw here, but it's okay, I just make a double draw. Okay, this is the first step. We find the nodes and then we make a straight line. We call that the forward line. Okay, and then we identify the loops. Okay, the first loop share one node with the CS here, so we make a loop from here to the summation junction here. Okay, summation junction is on the FS, so we make a one loop here. Okay, one loop without the arrow should be here. Okay, one loop here. Okay, so just now we have a straight line, so we need to put the arrow for the straight line. Okay, for each in between nodes. And another loop we have here, which is this loop, we don't have any block, so we put 1. Okay, why negative? Because this closed loop in the block diagram is a minus here. That's why HS and 1 is negative. Okay, be careful with these operation symbols. Sometimes they have a block diagram in the summation junction, they have a plus, not plus minus. So another one, we have this input, another input, the second input from DS. Okay, so one nodes for the inputs and one line to these nodes. Okay, and in between DS and the nodes summation, they represent the summation junction as a QS, so they don't have any blocks in between, so we just put 1 here. That's all for the conversion between, for the translations between block diagram and the SFG. Okay, and then you need to label all the necessary component, RS, ES, FS. Don't forget to label that. Okay. All right. Another one. I'm sorry. I left another one step is the gain. Okay, the block G1 and G2. Okay. So G1 and G2 is a block. So in the SFG, we consider as a gain on the line. So GS we put here, G1S we put here, and G2S we put here, because G2S is between QS and CS, G1S is between Fs and Qs. Okay, and another one for the HS, we put HS on this loop, okay, as a negative gain because of this operation is a negative, right? So let's say we have these examples. Okay, it's a bit tricky, especially on this part. Okay, they have a peak off point between this summation junction and G2. Okay, how are we going to do it? Okay, the first step, we need to convert this block diagram into the SFG. We have a G1 here, so the first thing we need to identify the nodes. Okay, input has a 1 nodes, output has a 1 nodes. Okay, and then how many summation junction we have? We have this one, and this one. Okay, this one as a 1 nodes. Okay, RS has a 1 nodes, and then the next after this summation junction, we have another summation junction, 1 nodes. Okay, after summation junction, we have peak off point, 1 nodes. Okay, 1 nodes. Okay, so after this peak off point, we have another peak off point, so we have 1 nodes. Okay, so after this peak off point, this is peak off point, we have another summation junction. Okay, 1 nodes, and then lastly we have a peak off point of the outputs, 1 nodes. Okay, so actually as you can see here, some a bit slowly in the conversion. So actually these V7s, okay, V7s for the line V7s, we actually, for the point of summation junction for V7, actually we have similar nodes here. Okay, this node actually can be combined as a 1 nodes. Okay, because HS here is considered as a gain for this line. Okay, gain for this line. Okay, and of course after this H2 become a negative. Alright, so we have another loop here, H1, and we have another external loop here for the H3. This one also can be considered as a 1 node. Okay, and H3 will be negative because of this one, because this summation junction here, they have more than 1 input. Like previously we have only 2 inputs. Okay, so not so much confused, but this one is a bit one by one step. Actually we can directly combine the nodes, but just need to be careful on this part. Okay, you can look at this. This is the actually the final SFG that you should get for that block diagram. Okay, So how you going to use the Manson gain formula? Okay, the component that you need to identify, basically you need to know the input nodes for the systems, output nodes of the system. Okay, so we need to know the component at first. Okay, the input nodes, output nodes, and then the path sequence. Okay, the path sequence. Here we have a path from x1, y1, x2, okay, y2, okay, and then the forward path. Which one is a forward path? Okay, so this one is a forward path. Okay, this one is a forward path. The forward means from left to right is a forward. This one is a backward path. We don't call that a backward path. We call that loop. Okay, loop. Okay. Uh, Normally we call that loops. This forward path, also the forward path, but since they have a connected into ending of the path is on one node with the other path, we consider this one as a loop. So next is a non-touching loops. Which one is a non-touching loops? The blue one is a non-touching loops. This one is a non-touching. Okay, why we call non-touching? Because this loop is not touched with the below loops. Okay, the top loops is not touched with the below loops, means that they don't share any of the nodes. And then we have a path gain. Path gain is that a, here I put a, normally we use G or H. Okay, here I put a, so we have a1, a2, a3, and a4, a5. That one is a path gain. Okay, and in the Manson gain formula, they want to get the forward path gain. Which one is forward path gain? Is a1, a2, and a3 is a forward path gain sequence of the forward path gain. Okay, and then the loop gain. Which one is a loop gain? a1, a2, a3, and a5 is a loop gain. Is a loop gain. Okay, or a2, a4 is a loop gain. Alright, so we go straight to the formula, and more technical, more mathematics. Okay, this is a formula of transfer function that used by the Manson's rules, Manson's formula. Okay, K is a number of forward paths. We need to identify how many forward paths. Okay, so and then you need to find the gain of the forward path. Okay, the gain of the forward path, and then delta K, and then we have a delta. We just go straight to the example. Okay, let's say we have this situation of SFG. It's straightforward to have a stable SFG. Okay, so how are we going to determine? By using the Manson rules. The first step is we want to identify which transfer function that we want to develop. You want to develop RS to CS, or you want to develop DS to CS transfer function. Okay, for this example, I'm showing you the DS to CS transfer function. Okay, so the K is 1. For this case, we have only one individual forward path. Okay, so then we can have a P1, because P is PK, so P1 is equal to 1 times to the gain. So what is the gain for this forward path? Is G2. So the P1 becomes G2. So we save that one for the step 2. So the next step, determine the individual loops. Okay, what is the individual loops? Okay, so here we have these individual loops, and these individual loops. So they like overlap each other. Okay, this situation we don't consider as a non-touching situation. So determine the pair of non-touching loops. Which one is a non-touching loop? They have a pair non-touching loop? No. They have a 3 non-touching loop? No, of course. Okay, so we skip these steps. Consider as 0. So step 4, determine the individual non-touching loop that does not touch the forward path. Which one is not touch the forward path? All the loops touch the forward path. Where is the forward path? Okay, all the loops touch the forward path. Our forward path just now, this one. Okay, so both loops touch this forward path. So okay, so we go back to the delta formula. Delta formula wants the sum of the individual loops and sum of products of non-touch pair loops, and so on. So which is sum of individual loop we can get from the step 3.1, and sum of the product of non-touch pair loop we can get from the step 3.2, which is no, we don't have a non-touch pair loops. Okay, so then we have loop 1 and then we have loop 2. Okay, so we need to sum loop 1 and loop 2, both loops in these equations. Okay, the summation here means that you sum the multiplication of the gain according to the loops. Okay, and then we can get the equation for the delta. So how about delta k? So delta k needs to have the components that not connect or not touching the forward path. So all loops are touching the forward path, so the component is 0, and then the delta k, because we only have one k, so the delta 1 is equal to 1 only. Alright, so then the input, we put the component, all the component inside the general formula of the Manson's rules. Okay, P1 we get from the step 2, delta from step 5, and delta 1 from step 6. So after we put all the equation, we can get the final equation like this. Okay, go to the next example, which is we have several non-touching situations, several independent loops, I can say here. Okay, like this loop, and this loop. Okay, so this is the final form of the transfer function for these systems. Okay, we go back to the step. Firstly, we need to determine the forward path. For this case, we only have one forward path, we only have one input, so that is a forward path for these SFGs. Okay, so the k is 1 again, same as the previous example. K is a 1, so determine the gain of the individual forward path, the gain. Yeah, alright, so the gain for P1 is G1, okay, G2, G3, G4 and G5. That's why they multiply all that gain, and that one is a P1. components. So individual loops, okay, individual loops as I marked just now, and I label here L1, L2 and L3, individual loops. Okay, and L4, don't forget for the L4, because L4 is from here, okay, for this case from here, including the forward pass components, some of the forward pass components, G2, G3, G4, G5, G6, G7 and G8. That one is for L4. So L3 only have a G7 and H4. Now why H is not negative here? Because H is forward. Okay, the arrow is forward, and here we don't have a we don't have a pull for the H4. So for the L3 it's positive. Okay, so same goes to the L2 and L1. Okay, why don't have a negative? Okay, because here we in the SFG it doesn't mark as a negative here. Okay, although this one is a backward. Okay, all right, determine the pair of non-touching loop. So pair of non-touching loop, which one the pair of non-touching loops? Okay, loop 1 and loop 2 not touching, loop 1 and loop 2 not touching. Okay, and then we have loop 1 and loop 3 not touching, loop 1, okay, and loop 1 and loop 3 not touching, this one and this one not touching. Okay, and then loop 2 and loop 3 not touching. Okay, how about loop 4? Loop 4 touching all the loops, because they share the some of the path. Okay, they share some of the path. Okay, like loop 4 share all the paths like G7, G2, G4. They share the path, they share the nodes. Okay, the next step for this step 3, we need to find 3 loops, 4 loops, 5 loops. So is there any 3 loops of non-touching loops? Okay, 3 loops that not touching loops. Okay, yes, we have 3 loops, 1, 2, 3, 3 loops that non-touching. So we need to multiply that loops again. Okay, all right, do we have 4 non-touching loops? No. Okay, so for the step 4, determine the individual non-touching loop that does not touch the forward path, does not touch or do not touch the forward path. So we have the forward path here. Okay, which loop is none of the group a loop that not touch the forward path? Okay, we have a L3 not touch the forward path. Okay, right, so determine the pair of non-touching loop does not touch the forward path. We don't have that pair of the loop. We only have single loop that not touch the forward path, and so on. So we skip the next step of the step 4. We jump straight to step 5, how to determine the delta. Go back to the formula of the delta, and then we bring the formula that we found into the delta like this. Okay, then we can get the formula for the delta. We go to the step 6 with the delta k. Okay, so we go back to the delta k formula. and then we bring all the components needed. Okay, so for this case we have only L3 for the component of delta k, and then we can get the final equation of the delta k, and then we put all the components that we get into the Manson rule. Then we can get the final equation of the GS, which is a CS that according to the RS input. Okay, I think that's all for this video. So thank you very much. Don't forget to subscribe. Bye.